from north for a station in the northern hemisphere. That's a point that I will keep repeating because it's very important in the logistics of selecting your site location. And also these ellipses, they are very elongated. They are not like a circle. They are much longer along the radial direction, and they are much thinner in the cross section. And the area of these zones, the reflection cranial zones, it's smaller for satellites that are this time. So for satellites that are near zenith, the reflection will be coming from close to the antenna in a small region. Whereas for satellites that are lower in the sky, not only is the reflection far from the antenna, but the area involved in this spectral reflection will get larger. Okay, but it's larger in a very asymmetric fashion. It's like a thin wedge that is much larger dimension in the radial direction. So keep that in mind when you are considering the obstructions around the site. For example, if you are in a coastal region and you have maybe a pier, you want to avoid the pier from falling inside the different. So we normally take the first zone just as a rule of thumb, and but it's not safe to just guarantee the first one falls on your surface. And one way to understand the geometry, and especially the internal geometry of this region, is to consider the delay, the reflection delay over the surface. Let's see if I get yeah, I was another picture here, but let's imagine for a moment that you get reflections from across the surface around the antenna. Right? You get a different delay for each surface patch. So we call that the bistatic delay. And the bistatic delay will find the spectral condition at the spectral point. It will be, first it will be least, it will be the smallest possible bistatic delay will take place at the spectral point. And secondly, it will be stationary. So that means the bistatic delay in the points in the vicinity of the spectral point have a similar bistatic delay. So the bistatic delay it changes slowly around the spectral point. And that's one of the reasons why the different zone is so important. It's because all the points that or the small surface patches that fall within this region, they are more or less emanating wavelengths, physical wavelengths that look alike each other. So if you take an average, they reinforce each other. Where from the spectral point, these physical wavelengths, they have very different phase. So when you take an average away from the spectral point, the result is near zero. That's a rough approximation, but just for you to get an intuition for why the spectral reflection naturally arises around the spectral point. It's because of this, because the bistatic delay is stationary around the spectrum point. And that's what I tried to represent in this figure. It's the antenna is at zero distance, and then there's a radial cross section going through the middle of one of these ellipses, and you get the least delay and the spectrum point. Now, the spectrum, the Fresnel zone, it's an offset from the spectrum point. The center of the ellipse is not at the spectrum point. You get one focus of the Fresnel zone at the spectrum point. So you may think of the spectrum point as the zero order. So when you get a complicated scattering environment, you cannot manipulate the reflection, this paper reflection, just digging a hole in the spectrum point, because you have all the surrounding surface regions contributing for the formation of this coherent reflection. So whenever you have a discontinuity, for example, if you have a soil surface and then asphalt, there's a very clear-cut transition between the two. So even if there are no geometrical discontinuities, if you have a material discontinuity, then you still have the creation of a diffracted wave, which is complicated to model and especially not very useful for retrieving the environmental conditions around it. So you want homogeneous conditions around the antenna and this scale of the first few Fresnel zones. And whenever there are changes, let this change be graded and not trivialized. All right, so uh, this may seem obvious that we are using radio waves, but people sometimes they overuse the word signal and forget that we're talking about physical stuff. So there is a radio wave being transmitted by the satellites that is very much like uh, the radio wave transmitted by remote sensing satellites. It's something that you probably saw yesterday. But what I wanted to have you keep in mind is the wavelength. So it's around 20, 24, 25 centimeters. And that will give you a range of in the reflections. And polarization, the transmission is right-handed, and when it gets reflected, it will normally contain both polarizations, right and left-handed, depending on the angle of incidence. So for near normal incidence, so for satellite near zenith, the reflection will change completely polarization from right to left. And if the same happens if you have a metallic reflecting surface, then it will change completely from right to left and polarization independently of the angle of incidence. But for natural reflecting surface such as soil and snow and water, you always get a mixture of the two polarizations, and it will be more left-handed for high satellites, and it will be more right-handed for low satellites. And that's one reason why this near grazing incidence is so useful for ground-based GNSS-R when you use a single antenna, because the direct transmission and the reflected wave, they have nearly the same polarization, nearly the same direction in the sky, and also very small delay between the two. So it's almost impossible for the antenna receiver to distinguish between the direct and the reflected waves, and you end up with a mixture. Or the traditional GNSS-R configurations, that's something to avoid, but for the GNSS-R, that's something that we see, because we always employ a single antenna and a single replica when tracking the signal. Now, the antenna plays a major role in selecting what which of the two polarizations will get accepted, and you start with an electric field that is a vector quantity uh, because it has the three components, the right-handed and left-handed, and then the antenna has an electrical length that is also vector quantity, and these act as weights. So the antenna can give preference to one polarization or the other. And normally these weights, they depend on the angle of arrival. So for example, for this antenna gain pattern, the blue trace is the right-handed gain, and the red trace is the left-handed. So for satellites that are near zenith, the intake is primarily right-handed, and the left-handed is negligible. For a low elevation satellite, for example, 5 or 10 degrees, the reflection for a horizontal planar surface will be at -5 or 10 degrees. And at these raising angles, the antenna response is very much alike across the two polarizations, especially for the small negative angles. So you end up with a mixture of the two in the voltage. So you have the electric fields, and the antenna will transform that into a voltage that gets propagated in the antenna cable to the receiver. So at this point, when your signal is no longer a radio wave and it's a voltage in the cable, then you can no longer have a mixture of the two, depending on how your antenna was designed. So in the optometry configuration, we have a single antenna and a commercial optical receiver that has a single signal replica. It's composite signal that it is the summation of the direct and the reflected wave. So as the satellites change direction in the sky, the reflection delay will also change. This reflection delay, it will be at least near the horizon, near zero at the horizon, and it will be maximum for a zenith direction. When the satellite is right at the overhead, the, the reflection travels twice the antenna height more than the direct wave. So we have the direct wave, it reaches the antenna, and then it goes down at the surface, gets reflected and then goes back up. So that's why we get 2 times the antenna height. That's the excess propagation delay. And here we always assume the propagation delay in time in seconds is multiplied by the speed of light. So we're normally talking about delay in meters. So light change height and mainly the satellite change elevation angle. Uh, the reflection delay will vary from 0 to guided by the wavelength. You get a number of cycles of the wave to the direct wave. So every time they are in phase with an integer multiple of the reflection delay, you get a superposition between the two, and then you get constructive interference. So they reinforce each other, they peaks get there's a constructive interference, and when they are out of phase, when they are 80 degrees and they usually have the same magnitude, the result is zero. You get them a destructive interference. And again, as the satellite rises, the phase difference between the reflected and the direct wave will change by uh, many times, many multiples of a wavelength, and you get an interference pattern. That's what we show in this plot on the bottom. We have a trend. This trend is basically the antenna gain pattern. And superimposed on this polynomial trend, you have oscillations. And the oscillations, you have more power when there is a constructive interference and less power when there is a destructive interference. And the signal may vanish during the destructive interference to the point that the receiver will have trouble keeping track of it. And these oscillations, they are more, they have a larger magnitude to lower elevation values because of the similar polarization between the reflection and the direct waves. So the antenna amplifies the two waves in the same way, increasing incidence, and as the satellite rises up, you get a dampening of the oscillation magnitude because there is more discrimination between the two polarizations, and eventually the oscillation vanishes. So these antennas that we use in GNSS-R, they have been designed for positioning applications where the reflections are something to be avoided because it causes a positioning error. So your antenna position will wander randomly because of these reflections. So normally surveyors, geodesists, and navigators, they will apply an elevation match that discards low elevation satellites because they are most likely impacted by reflections. So since there is plenty of data nowadays with the multiple GNSS constellations. It's a basic in positioning navigation and other applications to throw out data and keep the high elevation satellites, which are the ones where the antenna does a good job at rejecting reflections. So this combination of multiple paths gets the name of a multipath reflection condition. It is the vector sum of or the phasor sum of directly and with the consideration for the phase difference between the two. And that's what the trigonometric term in this expression represents. The oscillation arises from the simple sign of phi I, which we call the interferometric phase, the phase difference between the reflected and the direct waves. There are other functions here. P's, these are powers. So we have the direct power, the reflection power, and then both of them are involved in this oscillation. So, as I said before, the trend observed in the signal to noise is basically the direct power as reaching the receiver. So, after the antenna came out, so PD and PR already includes the antenna gains in each of them. Because the density of the radio waves reach the antenna before the antenna has an opportunity to amplify signals. It's more or less the radiation pattern of all the satellites that they were designed to compensate for the additional propagation distance so that the density reaching the antenna is more or less constant. So this variation it is caused by the antenna pattern. And for example, if you tip the antenna, it is upright, but if you tip the antenna, the this trend will change because again it is driven primarily by the antenna the reflected power is a function also of the antenna, but strongly by the composition of the reflected surface. So it's made of metal or water or soil, and not only the material composition, but also the geometrical, the small scale geometrical characteristics, so the roughness. And we'll see that in a moment. So the reflection delay in meters will be a simple function of the antenna height, times the antenna height, multiplied by the sine of elevation and this sine of elevation is the factor that causes the variation from 1 to 0 at the end and at the horizon. I think I have a question from my audience. Just a moment. I have to now my microphone. So the total metric fees will have a metric component that is the largest component, and it's just a and we will have a secondary component that is complicated because it depends on the polarization of the mixture, not only of the activity, but also of the surface material composition. Sea level monitoring. We focus on the electric component because it's by far the largest one, but we may end up with a small bias because we neglect the composition. So, for example, if the sea gets frozen, get the sea ice, and then your interferometric phase will change just because of the limited of the medium. And another important quantity is the interferometric power, which is the ratio of reflection power to direct power. And it will be a maximum of 1 near the horizon, because the polarization will be the same between the two waves, the two radio waves, and that will cause the antenna to accept both waves and amplify them in the same way. And the minimum interferometric power will be 10 to 0 at zenith. That's a rough approximation, and it depends on the material composition and the random reference. So that's why you have amplitude observed in signal to noise ratio that we are raising supplements. So, as I mentioned before, you have to keep in mind the carrier wavelength to split the surface and dimensional structure requires the large scale modulations will shift the position of your spectral point, and the small scale random reference on top of the modulations. It will primarily decrease the power because they remember the wavelengths is for the generation of spectral reflection. This reference randomizes these wavelengths in a way that even near the spectral point, the net results will be smaller than if you had a mirror-like surface. And we can quantify this by this formula, which uses the standard deviation of the surface height, sigma h, and it is scaled by 2 times sine of the elevation angle or sine of the raising angle to get variability in your interferometric delay. So let me go back here. If this cosine is shifting towards values slightly greater and slightly less than the average interferometric phase, then you get a decrease in this amplitude of your oscillations. And the random roughness can be static, like the topography, and they can be dynamic, like the wind waves, because you have this Fresnel zone running over the surface, and when we do the data treatment in GNSS-R, we take a whole arc that spans maybe 1 hour of data. So you get this effect observed over the whole span. The random roughness it has a more a stronger response for satellites because you get the radio wave illuminates both the surface, whereas get the reflection mostly from the surface peaks. So you still get mirror-like reflections from a rough surface to a low elevation unit. However, you may get an altimetry bias because the reflection is no longer at the surface average position, but it is by I. So keep that in mind. See how I am on time. And for altimetry applications, the height of the antenna above the surface is by far the most important parameter. It will change the frequency of your oscillations. It will not change the carrier frequency, but it will change the interference pattern frequency that you observe in the signal to noise ratio carrier to noise density. For this particular configuration, you have an antenna on maybe a 5-meter monument over ground, so the antenna height is not supposed to change. But if you have the same monument overseeing the sea surface, and you have heights, then the antenna height above the reflected surface will change, not because the antenna is going up or down, but because the surface is going down or up. So we call that the reflector height, or reflector depth, if you want, because it's never quality down from the antenna. And if you have the antenna altitude, for example, an ellipsoidal height or an orthometric height, you can get the surface, sea surface altitude or ellipsoidal height or orthometric height just with the sum of the antenna height, which is constant, and the apparent reflector height. And now for the response of the surface material, here is a simulation where I changed between dry soil, wet soil, fresh water, and copper, the damp surface. The antenna height is the same, the antenna roughness is the same, the antenna gain pattern is the same, everything is the same except the material composition. And you get that the interference pattern is shifting from because of that tiny phase component, the non-geometric component of interferometric phase that we go back here. So is sigma x, which is driven by the polarization mixture, that will be a consequence of the surface composition. So you even may get a change in the frequency of your interference pattern because the surface reflection is a complex value, is a phasor. It has a magnitude and phase. So the radio wave emanating from the surface will change in phase depending on the angle of incidence that's calculated by the Fresnel coefficients. And then when it gets mixed with the antenna response, which is also a phasor, or a complex number, has a magnitude driven by the square of the gain, and it has a phase driven by the antenna phase pattern, you get this nasty complicated picture. So this is all to say that altimetry applications are much easier because we pretend there is just geometry involved and we don't need to worry so much about the geometric component of your material. But if you want to monitor soil moisture, which is a compositional property of your reflector, then you need to consider these polarization issues. And I mentioned that even the interference pattern frequency may change with the surface material. And a clear example is, for example, when you have soil that is after a rain event, it is wet. And eventually the rain evaporates and the soil dries up. But the soil matrix didn't change itself. However, the reflective height or the apparent vertical distance between the antenna and the reflector may change. It will appear as if the reflection is coming from deeper in a dry soil and shallower in a wet soil. Just because the scattering center is a function of the surface is combined with the radiation response. Okay, so in the following, I will be focusing mostly on because it's the most mature application of GNSS-R. Yeah, even commercial applications already companies offering GNSS-R applications because it works well and it's relatively simple. And here, this is an example I normally give my students, which is the simplest possible altimetry retrieval in GNSS-R, which is basically counting frames or counting cycles. So your height in meters, here I divide by 1 meter to give this unit, and I will simply count the number of cycles. So let's start from a 15-degree elevation angle. I will count 1, 2, and 3 cycles between 5 and 15 degrees. So that goes in the denominator. It's a difference of sines, sine of 15 degrees and sine of 5 degrees. And in the numerator, we have the half of the wavelength multiplied by the number of factors. And voila, you get 2.11 meters. It's an altimetry retrieval in GNSS-R. So that's all we do. Okay. Of course, we don't do this visually, except for pedagogical purposes. So we have to automatize this to make it faster. And normally we do a spectral analysis. We start with an SNR that has a trend. We detrend it. just by empirically fitting a low-order polynomial. Then we'll get the oscillations. These oscillations, they still are have a dampening. We try to remove the dampening to get a sinusoid curve. And then we run like a fast Fourier transform or a long scatter periodogram, and we get a nice clear peak at the antenna height. You just have to be a little careful because this is not done, the input data is not in the time domain. Okay, we sample the SNR readings regularly time every second, 1 hertz sampling rate. But when we do the spectral analysis for altimetry, the independent variable is no longer time, but it is a quantity related to the observation geometry. So the frequency here air quote is actually your reflector height. So that's a very robust against the random noise estimate. If you want to do something more complicated, you can do instead of doing in a piecemeal fashion, as I said before, you can try to do it all at once. Fit a curve to the SNR observations, which is a sum of a trend and an oscillation. The trend is a low order polynomial. Here is a second order right? And then the oscillations will be a cosine function. And if you want to account for the dampening, this amplitude is not a constant, it's also a polynomial. And here is the trick for the spectral altimetry retrieval. Instead of using time as independent coordinate, you use this kz, which we call the vertical wave number. It's basically the number of cycles of the refracted wave in excess of the direct wave. So if you do that, then your picking your age parameter will naturally be the antenna height above of the antenna, the height of the antenna above the surface, with the caveat that it's not totally the geometric height that you would get if you were to a tape measure, or if you were to take a total station and take a site at the antenna and then at the ground. That's not exactly the reflector height that we have. It's more like an apparent reflector height, which takes into account the penetration of the red wave into the medium and all that complicated stuff related to polarizations. And you also have a phase shift term that may be useful for some applications like simulation. Okay, so this is a busy plot, but I just want you to keep in mind that we have a physical reality which is driven by the surface permittivity, by the antenna gain and phase patterns, by the surface roughness, and that you can use. But then we have an empirical model, which is just trying to fit a curve to your SNR readings. And the empirical model is what I have just presented, which is a polynomial and a sinusoid superimposed. So when you do this matching between the physical model and the empirical model, you get a clear picture of what is being estimated in each one, in each term. So let's just focus on the antenna, on the reflector height. The reflector height will be the geometric antenna height. Again, as if you were taking measuring with a ruler, plus the rate of change of your compositional phase component with respect to the vertical wavelength. So whenever you have the response, the surface response changing in phase with the angle of incidence, that may create a small altimetry bias in your regime. Okay? And that's all assuming you are in a vacuum, but you have the accident here that will also create a atmospheric bias. And this, I said, the surface is normally we assume the surface may be moving up or down slowly with the tides, but if you have a very large tidal range, like for example in the Bay of Plenty, we have a 20-meter tidal amplitude twice a day. So we need to account for the vertical velocity of the surface, the relative vertical velocity between the antenna and the surface. So, and this one turns out to be probably the largest non-geometric altimetry bias that you must correct for, otherwise you get additional noise. It's not random, but is systematic because it is a well-defined function dependent on the rate of change of height with time, so in meters per second, and the rate of change of elevation angle with time in radians per second. So even for the same surface, let's say you have the tide rising up, but you have an ascending satellite with a positive E dot, and you have another different satellite descending or setting on the horizon with a negative E dot, then you get altimetry biases of opposite sign because it is a formula that depends on the two rates, the height rate, the H dot, and the elevation angle rate, or the E dot. Fortunately, that's a very deterministic effect. You can easily account for it in a two-step procedure in which first we estimate bias, height of the depth of the surface, and then for example, spline curve to your time series of height retrievals to obtain H dot. We get E dot from the satellite orbit ephemeris. We know that very precisely. And then we can calculate this height rate fraction and subtract from your ascending satellites or add from your descending satellites. And when we do that, the tidal variation expected for a water site becomes much more well behaved. So then it took us some time to derive and realize that now it's 10-year-old correction. All right, so I believe I'm halfway I still have one more hour to do, is that right? I will shift my slide deck. Good, thank you. And
yeah, Philippe, you have one more hour.
good.
If you want, we'll take a 5 minute. Will be okay.
Well, let's do like this. I will go, I'll continue and I will stop maybe in half an hour so that we can have enough time for questions and discussion.
Okay. So currently time is 11. So okay. So till 5 we can meet by 10:30. After 5 minutes.
Okay.
Yeah.
Great, thank you.
So participants, we will go for half an hour, is it? And then, okay, you will continue for, oh, sorry for this. You can continue.
So we are taking a 5 minute break, is that right?
Are you taking 5 No. No, keep going. We'll go for half an hour and then we'll start for questions.
Okay, good. Let me shift my slide deck. Have you seen the slide, the title slide with the hardware on it? Good. Okay. So let's assume I have convinced you to do GNSS-R. What kind of instrumentation do you need? You can do this with the equipment. It has high costs. You get Linux files from it, so you get multiple cameras, multiple modulations. These antennas, they are large, they are bulky, they are heavy, they are sometimes more expensive. Thinking of the choke ring type antennas, and that causes a limited range of elevation ranges. You can still certainly do GNSS-R with genetic equipment. And that's something that annoys surveyors and geodesists, typing folks, because they like to believe that their antennas are perfect and they are so expensive that they will totally reject it. But that's not true. At low elevation levels, it's almost impossible to design an antenna theoretically that can reject reflections because of the similarities in angle of arrival, polarization, and delay. And we also have continually operating reference stations that have long archives, sometimes spanning multiple decades. So if it happens to be located near a natural surface, like a water surface or soil, then you can sometimes recover a 10-year, 20-year time series from these archives. That's a matter of luck because sometimes the genetic antennas are on top of a building, and not at a corner, so it's overseeing the roof the building roof and not on the natural surface that you can do something useful with it. So you are at the mercy of the size of these yours. Now, into a navigation type hardware option, they're much low cost. You can purchase navigation antenna for maybe $1. You do not get running spikes, you do not get interface, you do not even get a pseudo range measurements. You get only SNR data. And these come in what called NMEA. These antennas are much smaller. But the receivers tend to be single frequency because of costs. And the good thing about the navigation hardware option is you get a much wider range of elevation levels. Let me show you here for a genetic antenna, maybe above 30 degrees, you do not see any oscillations at all. And the useful range is probably below 20 degrees in this case. Whereas for a navigation antenna, oh my God, you get very deep phase even at high elevation. So that's very good for remote sensing applications and very bad for positioning applications. So there's a trade-off there. But since you are probably you're not sharing this equipment with anyone else, you can use the navigation antenna to do remote sensing of the natural environment much more efficiently than with the genetic antenna and at a fraction of the cost. And I mentioned here custom type. Sometimes you have dual polarization antennas, each output port connected to a different receiver. Excuse me. And the receivers they tend to be commercial off-the-shelf units. So it's again a minimum cost receivers, not only the antennas. So this is one that we put together a couple of years ago. It's available on GitHub. You have the bill of materials totaling $200. You can purchase directly from the store. We do not sell business. We just tell you what the parts you need. And with that amount, you get even a solar panel. So it's cheap enough that you are not concerned with the theft or vandalism compared to a genetic type of equipment. It can cost several uh, tens of dollars, tens of thousands of dollars. So these are some of the components that you can play with: an Arduino board, microprocessor, it records the data in an SD card. The GPS board is a field of the main board. It has an antenna here, an indoor antenna, but we do not use it. We take this coax port and connect an external antenna because we want the electronics to be sheltered from the rain and the weather elements, and you want the GPS antenna to be at a well-defined point because if you ever need to replace this equipment, if the antenna doesn't change position, the vertical reference frame is unaffected. That's very useful when you're doing a sea level measurement. You don't want to introduce a staff your water level time series when you replace the equipment. So as long as you keep the antenna fixed, you can replace the receiver and the geometry will not change. So that's how it fits together. We have tutorial, so it's like a 20-page step-by-step how to solder this. And it is an entry point for GNSS-R. You can certainly do this in master's project or even in a capstone undergrad level if you're really interested. This is how the NMA data format looks like. What matters here is the SNR value. It's an integer and custom firmware that the GPS chipset manufacturer was kind of make available so that we get one decimal place and that avoids quantization errors. So you don't need a gear fit, you don't need pseudo range, SNR is enough. We even get and as with here, but since they are also integer values, we needed them with the several decimal places, and that's better obtained directly from the orbit FNS files. And this is the kind of SNR data that you report with that equipment. Very deep fades with 125 dp. Even at high elevation numbers. And that's just a comparison between GNSS-R type gauge and a conventional gauge. And the correlations are normally exceeding 0.9 and is at a few centimeter level. It is precise enough that we even detected when the state government makes mentions in their radar gauge, so that we saw steps in the distance between the two time series. Not showing this here, but we can tell when they adjusted the zero level in their tide gauge just by comparing with this one. So it's a nice exercise in oceanography and or hydrology. GNSS-R station and a redundant sensor close to an existing station. If you want to set up your own station, we offer some guidelines. Many of them will be obvious after you read them, but it's useful as a checklist. For example, do not have an elevation mask. Some station operators they apply an elevation mask during the data collection, and it's not acceptable for reflectometry purposes. So and also maximize the visibility to the water, avoid obstructions, especially in your near field. You don't want any metal stuff within a few meters of your antenna. You even have Christine Larson keeps Hall of Fame of all the websites folks putting above your Genesis and they don't do that. So this is a checklist for generating useful data from your Genesis station. Assuming you want to compare it with the surveyors and geodesists, If you wanted to set up your own station using the navigation antenna, then we can even maybe turn the antenna upside down if you will. And my last slide is about applications. Do you see practical applications out there? I assume yes. So easy applications are altimetry. So that includes water level, either sea level or river level, and snow depth. I include the snow depth in altimetry because it's a geometric parameter. You observe background, and then you observe snow covered ground, and the difference in the reflector height between the two moments is your snow depth. And other non-altimeter applications, they are more difficult, and those are soil moisture and vegetation water content. So keep in mind when you are doing the data fitting, what parameters are usable for each application. I will highlight that in the following. So I'll start with the most difficult one, which is vegetation applications. Um, and normally we use the amplitude, the oscillation amplitude, because uh, the, uh, the vegetation, it acts more like a random roughness on top of the soil surface. It depends on the water content. If it is dry, then it is transparent to microwave or radio waves, and in this case you get a reflection from the bottom surface, the ground surface. When it's green, when the vegetation is green, then it's even difficult to answer where is the reflection coming from. It is somewhere between the top and the bottom interfaces. And here it's a nice culture that grows homogeneously to complete a plane. Um, but imagine if you have a natural plants like buckets that are scattered at random positions with the variability in height. So that's why it's more practical to monitor vegetation in terms of the mass they make in the spectral reflection in randomizing an otherwise coherent reflection. So we always assume that there used to be a spectral reflection before the vegetation existed, so the surface was sufficiently smooth, and then the seeds germinated and vegetation started to grow, and you get a more diffuse scattering emanating from this complicated medium. So it is complicated, okay? Let's go for an easier one, soil moisture. Soil moisture, but here's the trick. Probably background. So don't ever try to do soil moisture monitoring on a vegetated field because you will not be able to separate the vegetation moisture content from the soil moisture. Okay. So if you have grass, that's fine. Um, and here you have it was used a phase shift. Normally constrain the antenna height to a fixed value. So you run the series once, get a median value, or mean value of your reflected light, keep it constrained to a constant value and let the phase shift vary. And then the phase shift will nicely correlate with the soil moisture, the point that you see clearly when there is a precipitation event, you get these discontinuities, and then there is an exponential decay because the soil is drying up. So as long as the reflective target is easy, like not a mixture soil with little vegetation, then you can do soil moisture sensing with GNSS-R. Now, much easier target is no depth. This is an antenna model we set at a 3-meter top to never get the snow, and at that point it almost got snow up to the neck of the antenna. And we have these poles. These poles, they are red when a person that visits the site and gives us the green dots. And snow accumulates, and eventually the springs kicks in and everything will stop. Again, the reflection, we like to think it comes from the snow air up into the face, but it actually originates from somewhere within the snowpack, and this penetration depth depends on the angle of incidence. So if it's more shallow incidence, you get a more smaller penetration depth. It's more near near normal incidence, you get a deeper penetration. But that's something that has never been totally clarified. Nobody beyond geometric. And by far the easiest one is water, especially tides, because they vary by many meters at different sites. This is on an island. You can see high tide, small antenna height above the surface, and at the bottom you see low tide with a large vertical distance between the antenna and the water surface. And on the interference pattern, you see a high frequency at, at low tide and a low frequency at high tide, because it's the age factor in driving the cosine. So if this age is larger, um, the same satellite movement in the sky completes more cycles of interferometric phase when the antenna height is larger. And remember, this KC is the vertical wave number, which is sometimes your sine of elevation divided by the wave length. And we can capture the tides nicely, but notice the dots, they are not regularly spaced in time. We sample SNR, I said before, at 1 hertz, but the retrievals, they occur at random times, well, not random times, but irregular times within a day, because it depends on when the satellite decides to rise up and sets down on the horizon. Okay, it's predictable from the satellite orbits, but when you just look at the time of the day, it may seem it is irregular. So for the hydrologists and oceanographers, normally we sample the water level retrievals regularly spaced in time just after everything is done with the processing, we go on interpolation so that they get the data they are used to get with the conventional tire gauge. And the precision here will depend on your time range and also on your averaging period. If you do one average per day, you get a few centimeters precision. If you get one average per hour, you may be approaching 5 to 10 centimeters depending on the time range, and most importantly on the wind weights. Okay, so do not try monitoring on a surf region or when you have breaking waves, because these water brightness will totally annihilate your coherent reflection, and you get in your oscillations to the point that the interference pattern will be indistinguishable from random noise. So we do assume the water surface is relatively well behaved. So moving up or down is fine, but don't have a breaking waves. Get a place preferably. So these are some of the stations, all stations that we have set up recently on top of a lighthouse and on top of a silo. This region is in my home state. It was totally devastated in May last year by flash flood, and all the conventional water level sensors were destroyed. And that's why we are now putting the GNSS-R sensor on top of high so that it survives the next flood. We have also been experimenting with the narrow streams, and that you need to be closer to the water because remember the shutdown zones, they need to fit in the target that you want to measure. You don't want to measure the grass, you want to measure the stream. So get as close as possible, as safely possible. A bridge is a nice environment because with the navigation antennas, we get reflections from eye satellites that are very close to your foot. So if you can get on a bridge, then you get useful reflections from even from 60-degree elevation angle. So just to summarize the advantage, you have a length sensing or non-vertical geometry. It allows you to shelter the equipment from water and from theft and vandalism. So I like to call it a remote sensor. It's not like on an airplane or a satellite. It's still a proximal remote sensor in the sense that it's not underwater like a hydrostatic and it's not on top of the water like a conventional radar. It has no power consumption, so a small panel and battery can keep it running for several days since it doesn't transmit anything. Unless you have telemetry, right? These equipment I shared on GitHub, it doesn't transmit the data back. So if you want to do like telemetry via cellular network, GSM, then you get most power consumption from the modem, not from the GNSS modem. It's low cost because it's based on the off-the-shelf antennas and receivers with few dollars, you can, the $200, you can put the radio station with power included. And it has the promise of providing geocentric water levels. And that's useful for climate change monitoring because it allows you to separate the possibility of local subsidence from the water level area. And that, of course, assumes you are using uh, receiver that will give you care interface to the GNSS position. Now, limitations. It works on a station platforms station. You get a time series at that point only. So no drones or no satellites. There has been some limited demonstration from drones at low altitude, but the analysis is much more complicated. And from satellites, you that's not normally possible unless you get the shallowest possible incidence at negative elevation values. The time resolution is a big limitation of GNSS-R because it's not defined by the sampling rate. It's, even if I sample at 1 hertz, I only get an altitude. The only way to improve time resolution is to observe multiple GNSS constellations of GPS, plus GLONASS, plus Hindu, plus Galileo, etc. And you can put antenna high so that you get more oscillations in the interference spectrum, and then start to do some games with the narrow windows in your satellite part. But still, the time resolution is not much more like 1 hour, 1 second hour. You have to be careful with your site selection to avoid mixing vegetation with soil moisture, wind waves in water level, ice on sea level. Again, these they're complicated, but they're also an opportunity to do ice sensing or wind sensing. It's just messes up with your primary location. All you want is water level. It may not be possible if the wind is too strong. And there are a few biases that we sweep under the rug. They need more attention because of atmospheric refraction, curvature. We assume it's a planar surface. And we are also starting to see the frequency bias between 1 and 2 and 5. Minimum because of the antenna resistance. It will eventually need to be calibrated. It complicates the analysis, but eventually someone will know how to do it. A few data portals that you can, or this is the main data portal that you can visit to see all the continually operating reference stations that are useful for water level sensing. These are put together by Simon Williams. And I looked up there are no stations in India, and I suspect this is might be related to the data sharing policy. They found one station in Bangladesh, it was the closest one. So if you can get Indian force publicly available, you ask Simon to handle these stations. This is the zone mapping app that machine often put together. It's your first step when you are considering deploying a station. Look if you get decent reflections around the antenna, and I try to put close to where you are. Where I found you guys. And if you want to actually process your own data, be it RANX files from your data equipment or an MEA files from a low cost, you can use this software package. We started by Christine and then now has a large community behind it. We're invited to download the source code, to run it, to modify, to send improvements and bug fixes. And this is a quick demonstration of our first station here at home. You'll see this is a quick little product. You see the materials around peak, strong peak towards the water. Uh, and here in the top plot, just for illustration, you get the reflector height. And notice there is a step. There is a gap. Gap is the polar hole, the southern hemisphere, near 180 azimuth. And then there is a step in the altimeter retrieval. And can you get why when there's a step? It's about 2.5 meters. It's because we are sensing water and in a different azimuth you are sensing the ground. And the ground here is a parking lot. It's planar enough to get specular reflection. It is not as smooth as the water, so the spectral peak is not as strong, but to still get highly precise antenna heights from the ground at this station. And at the opposite azimuth, there is a building, so we don't get anything useful quadrants. And the last slide that I have to show you is in the online tutorials, we have recorded video tutorials how to run the software, how to process existing stations. So if you know of, it's a bit of a hunting game to find a good course nearby. Because some of them are close to the water, but they don't actually have obstructed visibility to the water, so it's not useful. But if you have a large course network in India, you may be surprised to find it useful ideas of opportunity based on GNSS-R. So with that, I thank you for your attention and open for questions.
Any questions?
Hello, friends. I'm Sushant. My basic question is, I've seen one of the models for the. So, what is the variable parameter in that one? Your first of the slide, in the first of presentation, there was a model for the light distribution. And you were saying that is 1 meter.
Can you speak with the microphone closer to your mouth, please?
In your first of the slides, the starting slide, there was a model. In that model, you have shown that the output of the height is around 2.1 meters. in your first of the slides. So what was the variable parameter in that one?
In this slide, this one,
In your first presentation, this one is the third presentation. The first presentation that you have made, in the basic of the SNR has been shown in that one, how we are getting the value of phase and the light.
right? So maybe we can run this. I think.
Dr. Rashmi is writing that in the chat box. You can see that. In the chat box, you have written that question. The question is like, there is a model that you have developed. That model is for the height estimation. Height estimation of the antenna height. The antenna height, the apparent height that you are calculating. The apparent height that you are calculating. It was showing that through the model, it was coming 2.1 meters. The apparent height was coming 2.1 meters. So, is there any variable parameter in that one? What was the variable parameter?
Okay, your first slide deck. Okay, for the choice. Let me shift here. Do you have this log number, maybe? The model for estimation. Okay, yes, yes. Okay.
After yeah, this one, this one. So, is there any variable parameter in that one?
Well, this is a simple model that considers only the geometry. So it's driven by the satellite elevation angle and the number of cycles that you counted and the Chiari wavelength. These are all the parameters involved. It works well for water level, but not for soil noise or other non-optometry applications. And this is a lot more important to get an intuition for how the optometry retrieval works.
Thank you, Philippines. Am I audible to you? Is that audible to you? The voice is audible to you?
Yeah, I need some help from the chat, please.
Felipe, we can will email you the question so that you can directly communicate with them. Will it be okay? Yeah. Yeah. Thank you.
Now we are having a 15 minutes break. We'll commence the workshop. Thank you, Dr. Philip, for the session. And now we are having a 15 minutes break and we'll commence till 10:15.
Yeah, thank you so much, Felipe. It was very wonderful, and I saw all the participants over here. They skipped their breakfast and their snacks, and they were still writing and noting down their applications, and that's what I was talking to Rashmi. It was more of a tutorial kind and application-based GNSS reflectometry than theory aspects. So thank you so much for covering it, and I appreciate your time. I know it is a midnight for you, so sorry for that.
Okay.
Thank you so
My
much.
pleasure. No problem.